Hi, everyone. Thanks for having us. I'll preface by saying we're both new to Valkey, and it's been a pleasure meeting folks in the Valkey community today. We're here to share a category of caching architectures that quietly does a lot of heavy lifting at Netflix called versioned caches. What we want to share today is this room knows demand-filled caching really well, but what we want to share today is a parallel story of a different paradigm that came to dominate our caching footprint at Netflix and what we think is worth bringing to a broader caching ecosystem. I'm Sunjeet. I'm a software engineer on the online data stores caching team at Netflix. And with me is...
I'm William. I work on the key value team, which actually is a database team, not a cache team. So thank you guys for letting me crash your party.
Thanks, Phil. All right, quick level set. Demand-filled caching is a dominant pattern in our industry. It's the right answer for a huge swath of use cases, and we run it at scale at Netflix too, at about 500 million ops per second. Demand-filled caching is powered through a few different interfaces at Netflix, including IPC response caching, Spring method result caching, behind the key value abstraction, and other abstractions like distributor counters and graph and time series, and also served natively as EVCache. We're not here to argue against demand-filled caching, but what we are here to argue is this. If you map our caching use cases by count and by data volume, versioned caching dominates at Netflix. On the left, in the gigabyte range, we have two technologies, Hollow and raw Hollow, that serves hundreds of use cases entirely in memory versioned. In the middle, we have demand-filled EVCache, and on the right, in the terabyte to petabyte range, you have OODM, and largest Axion-style EVCache deployments, which are versioned caches just remotely. 2 of the 3 regions are versioned, and one with the most use cases, and the one with the largest dataset volume. And that's the story. So what is a versioned cache? It's 3 key properties. 1, data is published as snapshots with deltas applied between versions. 2, there's atomic cutover between versions. So a consumer can transition from version N to version N+1 of the data set in a single operation, no torn reads between versions. And 3, within a version, data is immutable. That's it. Everything else is a consequence. So when we think about caching architectures, we think about them along these 4 dimensions. Footprint, how big is the data set, from gigabytes to petabytes. Consistency, how stale can the cache be, from milliseconds to hours. Latency, nanoseconds in process, microseconds for memcached, milliseconds for Cassandra. And finally, cost, RAM or disk. Each architecture lives in one of these 4 regions. And here's the map. Hollow and raw Hollow share the same tiny footprint, about 10 gigs compressed, but with different consistency profiles. Raw Hollow gives you near zero staleness, making the cache also being capable as a source of truth. EVCache lives in the microsecond latency band, and OODM is in the millisecond, petabyte, minutes, or hours of staleness corner. Next, let's look at each one of these a bit closer. Let's start with the 2 architectures for smaller datasets, where our version dataset offerings are more mature, starting with Hollow. Hollow is Netflix's open source versioned cache for small to mid-sized datasets. It has 4 key properties. It's a near cache, meaning dataset lives on heap in the client's JVM. It's total. Every consumer holds the entire dataset. It's immutable. Once published, a version doesn't change. And it's eventually consistent. So the propagation delay is in the seconds to minutes. The usage numbers of Hollow are staggering. More than 1 billion RPS is served at Netflix by Hollow, and the Hollow clients are deployed to around 120,000 nodes. 75 engineering teams use it, and it costs only $5 million a year of infrastructure spent. Since the entire data set is in memory, reads are nanosecond latency, there's no syscalls or network calls. But one might wonder, how big can these datasets be to fit entirely in memory? Well, the answer is more than what we might expect. Hollow is able to achieve orders of magnitude compression by using deduplication and ordinal references and bit packing. And some examples include an identities dataset that represented in Neptune DB was around 20 terabytes and compressed in Hollow is half a gig. And a movie metadata data set that was around hundreds of gigs of in its raw representation and compressed to less than a gig in Hollow. And how it works is producer apps periodically compute snapshots and deltas from upstream sources of truth via scans or incremental updates or transforms, and they publish them to some central storage. And consumers subscribe to these snapshots and deltas and apply them atomically in memory to serve a read-only view of the data. Consumers' business logic always sees a referentially consistent view over the entire data set in memory and never a partial state. Data is organized columnar and supports schema evolution. And because the data set is entirely in memory on the consumer, it can be indexed locally and queried any which way due to in-memory performance. And here's why we love it, because total in-memory data fundamentally changes the game. There's zero read path scaling because reads are local in-memory lookups, and the more clients you add, the more capacity you get for free. There's no data access pattern assumptions because the whole data set is on every node in memory, and any query is fast. So the publishers don't really have to design their data model around access patterns. This decouples the publisher and consumers teams, and data model and access pattern can evolve independently of each other without coordination between engineering teams. And finally, production data quality. Validators, region staggered rollouts, version pinning, history diffs, all because the data set is versioned. But Hollow consumers can only read. The next question is, what if I want writes? And that's where read after write Hollow or raw Hollow comes in. It's a total in-memory versioned, same as Hollow, but mutable, with read your writes consistency. And this property makes the cache also capable of being the source of truth. There's no separate database. It's built on top of the same Hollow infrastructure. How it works is writes go to a small raw Hollow clusters, which replicates them to clients immediately and compacts them into snapshots periodically. While compaction is in flight, recent writes are held per client in an overlay, so reads are still in memory against a base Hollow snapshot plus a small overlay. If you need stronger, consistent reads, you make a remote call to the raw Hollow cluster to get consistent. And the consumer model is largely unchanged. Like Hollow, it's total in-memory typed API access. But, I think I switched back that time. And why do we use raw Hollow? Because it eliminates an entire database tier. You used to need a source of truth plus a Hollow producer. Now it's one system, and from this new source of truth, you read at eventual consistency, effortlessly at scale, because every read is an in-memory read for clients. It's become the default data store and cache for enterprise scale or hundreds of gigs of data scale at Netflix, and there's about 500 use cases internally and increasing. So Hollow and raw Hollow work well for small and mid-sized data sets, but what happens when the data set is too big that it doesn't fit on memory in every box? You still want versioning, things like atomic cutover, validators, and rollback. You just can't put the whole thing on every JVM. That's where our first inspiration comes in. It's application-level versioning built on top of EVCache, which is not a versioned cache. EVCache is a distributed cache built using memcached and spy memcached. And Axion is one EVCache cluster, and it's the largest one that we run. And it powers Netflix's recommendations by serving member-keyed ML facts in memcached ext store. The scale for this one data set is 8 petabytes on disk, 250 billion keys, and 2,000 nodes per replica. Axion implements versioning on top of EVCache at the application level. Periodic Spark jobs compute facts and store them in S3 for durability and EVCache for low latency querying. Entries are keyed by date. Each day's data is immutable once written. Version cutover happens at the app layer. 18-day trailing versions are held in the cache. So you get versioning, but only as a convention layered on top of the cache, not as a first-class primitive. We're not listing this as a success story for version caches. We're listing it as an inspiration. When versioning is an application convention, two things happen. One, incident response involves multiple teams. We've had TTL bugs that required custom recovery. And two, versioning at app level is hard to scale. The next architecture, which William will talk about, is about versioning as a first-class platform feature, not an application convention at petabyte scale. Over to you.
Excellent. Thank you very much. Yeah, so I'm going to talk about the system we call OODM. And OODM really fundamentally represents the other side of the spectrum from Hollow. So when the data sets are really large and can't compress down to be in memory on every node, and you need them to be remote, kind of like the Axion use case, although maybe evolved from the Axion use case, we can use this system OODM. And what is OODM? It's a kind of a funny word. If you ever are on a video call and you're talking about OODM and there's a transcription, likely it'll think you're saying udon, but it's actually not a noodle. It's just an acronym, and it stands for online or offline to online data movement. And that name is kind of comes from the original inspiration, which is we had these data sets that were computed offline. Like someone earlier mentioned a MLP, like a feature store use case, machine learning feature store use case. That's one of our users as well. And when you compute these big data sets offline, but you want to query them with low latency, you want to take the result of that compute and load it. So that was kind of our original idea. And what was challenging was in order to move large data sets online, you'd have to scale up your database big enough to accept all the writes in a timely fashion and make progress. What we did is introduce this idea of versioning as a kind of first-class element, and then design a system around how moving data in terms of versions in a fully isolated way. So instead of loading the data into an existing store, you can load a version of the data into a new set of infrastructure, and then you can move metadata around as a pointer to kind of evolve your serving layer across the versions. And what's kind of critical about this is two things. The first is you separate the preparation of data from the serving of data, because the kind of fundamental thing is when you know what your data set is because you computed it offline, there's no reason to say write it into Cassandra and recompute the LSM because you know what the LSM should be at the end. You can just do that up front. And that's exactly what we do. And the second is you can scale this kind of solution very effectively. And it's because you're decoupling the write path from the read path, and you are taking away a lot of the assumptions databases have to make or a lot of the challenges databases have, and instead you kind of have this problem of I have a lot of data, how can I bin pack it efficiently among the infrastructure I have? So that you can very efficiently pack things, you can use a lot more disk than you traditionally would on a database, and you can achieve high scale. So let me dig a little bit more into some details here of how we're actually doing this. The first thing is the interface we're providing, actually I'll call out on the first slide, is kind of from the right side is this list of versions. You are creating offline a set of versions and you're giving us those versions to load. On the read side, your API is just this KV API. It's a kind of unified put and get API. And what we back it with is where we take advantage of this versioning. So there are kind of two flavors. There's first the Cassandra flavor, where we can load data that we've pre-computed into Cassandra SSTs into a live Cassandra cluster and load it into the LSM tree. So while you're doing mutations on your Cassandra cluster, you kind of get this big influx of data loaded all at once. And it's loaded very efficiently because we can just download large files in a big batch. The other flavor is the read-only, and this kind of is where we start to get into the real power of versioning, because instead of loading data onto a running cluster like we have to do with Cassandra, we can actually just spin up an entirely new cluster, and we can pin the CPU to 100%, downloading as fast as we can. We can scale out really, really wide if we have a really big data set and we want to load it quickly. We have a ton of flexibility in how we load that. We can truly abuse that infrastructure without having no impact on the serving data. So then once we have these two versions, now we can kind of control how clients move their traffic across these versions. So this also allows us to do very powerful things like validate the new server group that came up with big swaths of smoke tests and integration tests and performance tests. We can roll back really quickly. If for some reason something goes wrong, as long as we keep that old set of infrastructure around, we can just move a routing pointer and fall back to the old version set. So and all of this is hidden behind a single unified KV API for our clients. So yeah, just to summarize what we achieve here, the bulk delivery makes writing data much faster, much more efficient. the versioned nature of data gives us these semantics that allow us to do kind of advanced validation, advanced rollback. That's really not possible in a system where you're consolidating all your data into one place. And finally, you get to take advantage of the familiarity of these versioned semantics, which is we all deploy code. We're all very used to deploying code artifacts, and those are kind of version sets of data. We can take those same ideas and apply them to actual data sets, not just code artifacts. And so you can have pipelines that validate. You can have roll forward and roll back pipelines. And these are ideas that are familiar to developers and kind of can immediately be taken advantage of. So I'll hand it back to Sunjeet to wrap it up.
Thanks, Will. So let's zoom back out. What does this version caching paradigm give you? There's no mistriggered thundering herds, no stale sets from concurrent fill races, and no cache source inconsistencies, since the cache is a point-in-time snapshot of the source by construction. There's no cache misses because the cache is pre-filled, no cache invalidation, new versions replace old ones atomically, no cold start, consumers bootstrap from the latest snapshot. Referential integrity is intrinsic. Atomic transitions mean you'll never see a partial state. Validation is straightforward because every version is a discrete addressable artifact. Pinning, hold any consumer to any version. And history, diff any two versions of your data set. Most of these problems are demand-filled caching are problems that demand-filled caches have to solve at runtime, often imperfectly, and version caches can simply sidestep them. But it's not free. There's real costs. The main one is propagation delay, seconds to minutes to hours between when a producer writes and when a consumer sees. So if you need real-time, mutable, record-level, high-throughput mutability, this is not your paradigm. Producer complexity and system complexity for building things like version coordination and snapshot bootstrapping are also real costs, but those are engineerable. Which brings us to why we're standing in front of you specifically. What if Valkey embraced versioning natively? 3 primitives would be enough to start. 1, a way to atomically install a binary blob representing n pre-built keys into a running cluster, bypassing per key write overhead, to allow loading a data set produced, say, offline by a Spark job into a running cluster fast. 2, atomic cluster-wide swap of a logical database or a named key space. And 3, bulk drop of a logical database. With those 3 primitives, apps could get benefits of versioned caches without having to rebuild. That's our talk. Thanks. Our handles are on the slide. Thank you.